Hello everyone, this is Anil Kumar with my groupmate Rice, and we are going to explain our FIP project titled Load Frequency Controller Design on governor side using PSO algorithm under the supervision of respected Dr. Qasim Ali and co-supervised by Engineer Ghulam Akbar. So what is inside this project and what we have done so far in this project. So we will be having overlook of that project. So let's get started. So, explained earlier, this is the title of our project FIP, and these are the group members. So, let's get started. The flow of our presentation. First of all, we will be having the introduction of our project, then the literature review we have done, and the problem statement, which project, the objectives of our project, then system modeling, then the introduction and basic concept of the particle swarm optimization technique, then results and discussion of our project and future work and recommendations. So first of all, the introduction, the frequency and voltage, the main quantities of any power system. They must remain at nominal values or the normal values during the operation of an electric power system. So what happens that whenever a disturbance occurs, the load varies with respect to time. It affects both the frequency and the voltage. But frequency mainly is highly affected by the active load, and the voltage is affected by the reactive load. So the active power or the frequency control is called the load frequency controller, which is our objective. So what we have done one step further, that we have merged two power systems together to highlight the research hotspot of today's research, and that is the renewable energy merging into the conventional energy sources like PV storage system, battery storage system, fuel cells, all the non-conventional sources of energy which we are having nowadays, and merging them with the conventional sources like thermal power system or the diesel engine or all the conventional systems, which will do what, that it will increase our power systems efficiency, and the load of the power system will be distributed among two different power systems. And why have we chosen the hybrid power system? That as we all know, that the research hotspot or the main theme of today's world is that it should be, everything should be pollution free, everything should be clean, and the energy, mainly the electrical energy, should be in clean in terms of their usage, desired demand. So let's get towards the literature review. The literature review help us a lot to do our research, to help us our guiding factor. As a guiding factor, it helped us as a guiding factor, and we have done that. We have seen that many researchers have highlighted these topics, and they have put up their efforts to show their efforts that what can be done in this field. So first of all, like Adil Usman, we got to learn through that a simulation study is carried out to the understand of operation of load frequency controller by developing models in Simulink. So the developing phase of different models in the Simulink software mainly helped us through the Adil Usman's research paper. Similarly, like that, many research papers we have gone through helped us in understanding the PID controller, understanding the PSO algorithm, understanding the hybrid power system, understanding of each and every aspect which we can understand and which we need to understand for our FIP project. So these are all the literature review helped us a lot and guided us to achieve our goal. So these literature reviews are shown here, and like this, PSO is used for optimization of control gains of the proposed hybrid system. So PSO applying on the hybrid system is our main theme, or we can say that load frequency controller of any power system is our main theme. So problem statement comes out that the high frequency deviation, as the any difference or any disturbance occurs in the power system, like I said earlier, that the load varies with respect to time. You cannot control that. Like in Pakistan, load varies with respect to time, and in all the world. So high frequency deviation occurs mainly due to the load changes. So the if the deviation is so strong or it is so high, then system may be collapsed, and so that's why we are in a bounded condition that the voltage or the frequency must remain intact to supply of our energy without any disturbance. So the limitation of conventional controls, like many use PID controller, many use PI controller, each and every controller, what is the main limitation? That they are, if they are done so far for the manual tuning, then the slow and lack of efficiency in handling system non-linearities. So the merging of artificial intelligence based control techniques or the algorithms with these controllers mainly is the theme, that the controller's efficiency or the controller's handling capability of any disturbance may be increased or may be improved. And the optimal response of the any load frequency controller scheme must be applied at both sides, like on the generator side and on the load side also. Because a generator's limitation is that a generator, if a generator is of 2 MVA for example, then it will only supply 2 MVA, it will not go beyond its limit. So that factor comes, that load should also be controlled using modern algorithms or the techniques, maybe wherever the necessary is. So for our research project or our FIP project, we have done so far the generation side frequency control. So the modeling of first of all the isolated power system based on transfer function. So it contains a governor, turbine, rotating mass, and load. You can say the load, which is mainly the factor of disturbance of any frequency. And this is the control loop. You can see the 1/R factor, the droop or the loop control. And here is the reference. We can say that in Pakistan, it is 50 hertz for the reference of frequency. So the reference of our topic will be 50 hertz. And this delta PL is the disturbance mainly, which causes the disturbance in any power system. Then modeling of Thailand, because as stated earlier that the project is basically a hybrid system. We have to merge two systems, solar PV hybrid system and the thermal system. The merging of these two systems is done by the Thailand, because Thailand is the main factor which shares the power between two different power stations. So the transmission line that connects an area to its neighboring area is called a tie line. Power sharing between two area occurs through these tie lines, like load frequency controller name signifies that regulates the power flow. Power flow between these two power systems or any other power systems. The neighboring power systems are connected through the tie line, and tie line shares the power of these two different areas of the power system. First, the frequency difference of the frequency difference or the deviation, you can say, is of the second power system. These two are the sum or the differentiated, and this is the synchronizing factor T1 2. This is the synchronizing factor of the modeling of the tie line, and this is done by the Laplace transform, and they share the power. Here the power is the main component which comes out of the modeling from the tie line. So modeling of the tie line is done, modeling of the isolated power system is done. Then we have to model the PV system. All can be shown in this transfer function shown here in the block. So the equivalent transfer function model of the solar PV system can be understood of this transfer function. So we have the hybrid power system model, because we have the thermal power system transfer functions, we have tie line, and we have the PV system in form of AC. So we can interconnect them. The interconnection of this system is like this. The solar PV system, like we have told here, that this is the transfer function of a solar PV system, and this is all the model of the isolated thermal power system. And in this case, it is not isolated now. It is connected through a tie line, which is sharing the power, and the difference of the frequency is going into the tie line, which is output is the power. So let's get through it. The implemented model, same model, the isolated, first of all, the isolated model in the MATLAB Simulink, which is shown here, that this is the model of this is the model of the isolated power system. The same model is depicted here in the MATLAB Simulink software. The governor, turbine, and inertia and load. Here, the error is being read And this is the droop control here. This step input depicts the disturbance of any load, and here we can read the our frequency deviation. Then this is the isolated system. This is the interconnected system. You can see this is the thermal power system, and this is the solar power system. A disturbance is added here, a disturbance is added here on both the power systems. Here main difference is here is PID controller, here is also PID controller. First of all, see that here is only one PID controller, but in the interconnection PID controller are double, because as we increase the power systems, then each and every power system needs a controller to control that power system particularly. So this is the tie line, difference of the frequencies, and here power is sharing. So these are the models of the transfer function based models of the hybrid and isolated power systems. And finally, the generator load model. Like this is the synchronous generator, and if we go into the specifications or the parameters of this generator, then it is a synchronous generator of 2 MVA rating running at 600 volt. This is a 1.04 volt obviously needed for the excitation, mechanical torque provided with the PID controller. This PID controller, the PID controller gains KP, KI, and KD. The PID controller gains are set with the PSO algorithm. What is PSO algorithm? It will be explained. And here the error is being read, the reference point is, and these gains are summed up, and PID controller is designed, and it goes with the mechanical input. So here the RPM of the generator can be read, and electric and power sharing of the generator, and it can be read through these scopes, and we can analyze them. So this PSO algorithm and further the results and analysis of our project will be explained by my Reis.
Okay, this is Reis here. Now I will be explaining particle swarm optimization technique and the result and analysis in the conclusion. The previous part is explained by me very well. Hope you all understood what he said. So first of all, I will talk about particle swarm optimization technique. So it is an iterative optimization technique. Basically, this was proposed by James Kennedy and Russell Everard in 1995. So what is inside particle swarm optimization? Let's see. Basic idea of particle swarm optimization. First of all, we randomly take a number of particles, agents of particles that constitute a swarm, moving around in the search space looking for the best solution. We will define a search space where to find, and that will find inside the search space where the optimum solution lies. So what we do, each particle in such space adjusts its flying according to its own flying experience as well as the flying experience of others particles. So each particle communicate with each other particle. So all particles will be communicating with each other. This is suppose a function. We see air is the global minimum. Suppose this is one particle and this is one particle. So both this particle is moving in this direction and this particle is moving in this direction. Suppose particle is in this position. So it starts from this position and it comes here. So here it sees that it founds a minimum which it didn't get in previous positions. So this is its personal best. This is its personal best. As it moved towards this position, it doesn't get any good point up till here. But when he moves here, then he gets a better and better point until he reaches here. It gets a best point, and it keeps moving there until it reaches there. It gets a global minimum. So it is the global best. It gets a global best. Particles move toward the point where the optimum solution exists. So in this case, we were finding the minimum of the function. So minimum exists here. So it got the minimum. So particles communicate with each other and learn from their previous experience. So that's how that is what basic idea of PSO. So some how fast particles should move and in what direction particles should move. There is mathematics of particle sum optimization for that. Velocity and one is for position. So velocity is for how fast or how far particle should go, and how fast should particle go, and a position is where particle should go in the next iteration. So that is decide on these two equations. This is the flow chart of the PSO. First of all, what we do, initialize the PSO. And initialization, what we do, we randomly initialize particle. Randomly initialize particle. We initialize the velocity and position of the particles. What we do is the position. First of all, we uh, initialize that's through random numbers. We initialize the particles through random numbers, and then we evaluate the fitness function. Also, we call this objective function for each particle for local and global best solution. Each particle we take, we put in the fitness or objective function, and we calculate what value it is giving, and we find the personal best of each particle, and among these particles we find the global best, which is best among all of the particles. So there are mainly two iteration we run here. This is the two iterative process. Now what we do, update the velocity of each particle as explained in the previous slide according to that equations, and then as we updated the velocity of each particle, then we update the position of each particle. Then we have some stopping criteria. Suppose we have some we set number of iterations. There are two stopping criteria. One is our number of iterations and other is our minimum error. If minimum error or the minimum error, the best value of fitness function or objective function is reached, then we may stop. If uh, or if number of iterations are finished, we may stop. So the flow is stopped and we have got our optimum solution. If no, then we may go to next iteration, and again we go through these process and again we check. So this is the iterative process, and goes and goes and goes and goes until we find a optimum solution or number of iterations are finished. So coming to next slide. So as explained by Anil, we first of all took the isolated system. So isolated system, we gave you the general block diagram model or transfer function model of the isolated system. Now what we do for simulation, we need some parameters. We have to put those parameters so that our simulation may run. So these are some parameters which we put in those transfer function so that we get a particular transfer function or a particular system, so that we run that system. Some we did some tuning of the PID controller which we fed there. We did some manual tuning of that. This tuning was done through it and trial. We didn't use PSO algorithm, any optimization algorithm. We put these parameters in PSO algorithm. Next, we have interconnected hybrid system. Now for interconnected hybrid system, what we need? The same thermal system we took as explained in isolated system, same thermal system we took, and a new thing comes here is the T12, that we put 0.2, and we took a PV based system, so we gave a transfer function as explained by Andy. We gave a transfer function is fitted in the model, and these parameters are put in model and model is run, and we applied PSO algorithm for tuning of the PID. So what we got the values of after PSO optimization are given as these. Now we run that a developed model on generator load model. We simply took a synchronous generator and put loads on it and shared some load, after which we saw the results. To the next. What were the results after our simulation? These results are for isolated system. The following three graphs show results of simulation for isolated system when PID was tuned by manual tuning. These results are for manual tuning. The following graphs show actual frequency. This shows us the actual frequency. This shows the frequency deviation in Hertz, and this shows the frequency deviation in PU. As we can see, there are large undershoot in the graphs, and settling time is 7 seconds, which is very huge. And up till that time, our system may go to brown out or blackout, whatever. So, as we can see, this is not the best results. We didn't get the best results. The following three graphs show the result for isolated system when PID was tuned by PSO. The following graphs show actual frequency deviation in Hertz, and frequency deviation in PU as shown in the sequence. The response of controller is now quite better. There are large, undershoot like swingings. It has only one undershoot, and it comes to the value within 3.5 or 2 seconds. It comes in its original value. After 3.5 seconds, it is almost steady. It is steady. But as we can see, within 2 seconds, it is near the optimum value within the limits. A maximum after 3.5 seconds, it is already steady. So it's just this was our iteration results. So the following graph show the result of PSO algorithm. The x-axis show number of iterations and y-axis show weight of the objective function, that is integral of absolute error. As it is shown from the graph, within fifth iteration of the objective function waves is reduced and got to a constant value, as we can see here. So following three graphs show result of simulation for interconnected hybrid system when PID was tuned by PSO. As this is the interconnected system, that there are more transients and ATC might occur because we have interconnected a PV system, and it may not give quite stable results like before isolated system. There may be tie line errors, etc. So it may take some time to come to a steady state, but it will come to nominal value very quickly because PSO gave us the best parameters. The following graphs show actual frequency deviation and arts and NPU respectively. The graphs are a responsive system when there is maximum deviation, but still response is quite good. System comes back to allowed limit within 5 seconds. So, and it comes to stability again. Next, this is for generator load model. So the following figure shows response of generator load model results without controller. As it can be seen, when a disturbance occurs, load disconnects, rotor speed start increasing and goes beyond limits. This was the without controller model. The following figure shows response of generator model result with PID controller by PSO tuning. As it can be seen, when a disturbance occurs, load disconnect, rotor speed start increasing, and controller comes in action and bring it back to nominal value. And this is the best response given by PSO algorithm. So our conclusion: controlling power system to meet customer demands is difficult challenge that drive the development of optimal controllers because the power may increase and decrease according to the customer demands. There should be our power system should be able to easily track the power supply such as frequency and voltage maintenance. The construction of controller employs a number of optimization techniques. There are a large number of optimization techniques, but we compared and found that PSO algorithm is the best, and we use PSO algorithm. PSO algorithm is used to tune the parameters of PID controller or controllers, as in the hybrid model, interconnected hybrid model. To demonstrate the process, an isolated system, an interconnected hybrid system, then a generator load system is considered. The objective function was the integral of absolute error, which we gave to the uh, PSO algorithm. By varying the load, different plots of the frequency division were obtained, and we gave some disturbance to the systems. So, what were the results? We took those results. Also plotted and observed where the effects of parameter variation in the device response. The superiority of this approach over the controller tuning method can be illustrated by comparing the error values. What may be the future work? The benefit values of controller for two area interconnect system are obtained using only the PSO algorithm in this study. As a consequence, it can be used in a multi-area power system. Other algorithm for obtaining controller values can be considered, and comparison between them can be made. We may use other optimization algorithms and compare those results. And we took only two area, one PV and one thermal power plant. We may take more than those. We may take the wind power plant, and we may take other renewable sources and expand our research. So there is vast research areas in this topic. So we can go further there, but our research was up till here.